I'm just going to quickly delete this stuff over here because I'm going to go through that again. Okay, our question says a 1.45 kilogram toaster is not plugged in. Okay. The coefficient of static friction between the toaster and a horizontal countertop is 0.345. Very creative number. To make the toaster start moving, you carelessly pull on its electric cord. For the cord tension to be as small as possible, you should pull at what angle above the horizontal? Okay, first off, let's start with a diagram because diagrams are somewhat useful. So this is going to be my countertop, okay? We're going to have the block right on top of it. We're going to call it M. And we're going to have the horizontal, which is going to be because we are assuming that the cord is attached somewhere over here in the center of the side of the toaster. And then we are going to have our cord being pulled this way at some angle theta. Now let's draw that free body diagram for this because there's a little bit that we have to consider here. We have our N, which is our normal force. We have our downwards force, which we denote as mg because it's mass times gravity. We have our Fs because it's our static friction. This can also be written as Mus, okay? I know I use that a lot in some of the other questions. And then over here, we're going to have the horizontal, okay? This is just an axis, so I did it a different color. Switch back to black here. And we're going to have the T tension like this with the theta like that. And this is called T, okay? So just remember that this is going to be T. And that is going to be what we're going to be using to solve. Now, I'm going to start off with a very simple equation. Probably most of us know this one, and it's the equation for a normal force, okay? N is equal to mg minus T sine theta. Now, never mind the fact that we can calculate mg. We're not going to do that because our second equation that we're going to use, and I'm going to set this off to the side because we don't actually need this quite yet. The second equation that we're going to use is for static friction. Because the equation for static friction, it's Fs, okay, come on, that's a really cute F, is equal to Mus N, okay, this is the N of T. So what can we do? We can actually sub in. So this becomes, guys, I'm just going to draw a normal F. F of S is equal to mu S. And then we can open up brackets and we can say mg minus T sine theta. Okay, we're getting somewhere. Now, we have to consider for the toaster to start moving, the horizontal component of tension, which would be, guys, I'm just going to draw a little squiggle. Tx is equal to T cos theta. This must be equal to the maximum static friction force, which is this little thing right here. Okay, that's the maximum static force. So, interesting. Now, we did this with the N. Maybe we could do it again. Oh, we actually can. So we can substitute instead of Fs, we can say T cos theta is equal to Mus mg minus T sine theta, close bracket. And then we can simplify this, and you know what we get when we simplify this? I'm going to just scroll down. Okay. We get T cos theta is equal to mu. Why is my mu starting to look like a Y? I promise it's not a Y. Mu S mg, because we are factoring it out over here, minus mu S T sine theta. Okay, and then we can actually move this all over. So this becomes, I need to actually do those equal signs somewhere else. Okay, this becomes T cos theta. We factored out the T here. T cos theta plus mu S sine theta is now going to be equal to mu s mg, which then we can see that cos theta plus mu s sine theta reaches its minimum when tan theta is equal to mu s. Okay, this is literally all it is, guys. All right, it all boils down to tan theta is equal to mu s, and then we just plug that in. So this becomes theta is equal to tan negative 1 times mu s. Plug that in, you should find a value, and that is how you solve that one. Now,